Look at this cross-section of a moringa seed. The tree dedicates massive resources to producing these kernels, engineering them into a dense matrix of lipids and proteins designed for quick tropical germination. To extract those lipids for industrial use, the standard method relies on brute force. Facilities feed these seeds into a continuous mechanical screw press. But mechanical pressure has a hard limit. The screw press cannot fully rupture the rigid cell walls, leaving roughly 15% of the oil trapped within the residual seed cake. Reaching that trapped oil requires us to soften the hard biological shell protecting the kernel. Physical force alone cannot penetrate the cellular structure. This is the integrated yield and value function. We use this mathematical framework to optimize industrial processing. Total system value is the sum of the extracted yield multiplied by its market value, minus operating and capital costs. The primary objective of any biorefinery is maximizing the yield variable. We have to extract every drop of oil, but we must do it without causing our operating costs to grow at the same rate. Mechanical constraints strictly cap profitability. To extract the total value held within the seed matrix, we need a secondary intervention. The most intuitive way to soften the seed is introducing moisture, typically by soaking or fermenting the raw material. However, this triggers a biological defense mechanism. The second water touches the seed, dormant lipase enzymes wake up. This is the glyoxylate cycle pathway. Once activated by water, these lipases rapidly cleave the stored triglyceride lipids into free fatty acids, or FFAs. High levels of FFAs alter downstream chemical processing required for biofuel. When entering the base-catalyzed transesterification stage, they react incorrectly. Instead of yielding combustible fuel, they undergo saponification. The chemical reaction turns the entire batch of fuel into a useless, soapy waste product. Processing high FFA oil forces operators to add a mandatory acid pretreatment phase just to neutralize the oil before it ruins the main reaction. This added step requires more chemicals and more time. It drives up operating costs and attacks the efficiency of our yield function. Treating the matrix purely mechanically leaves yield behind. Treating it chemically by soaking introduces contamination. True optimization requires us to decouple these forces. This requires the Drueppel Gemini approach, a two-stage modular cascade designed to separate fast physical extraction from slow biological extraction. This is the factory architecture where we will physically map out the concept. We place the first stage of the cascade onto the floor, Module 1, the mechanical screw press. For our starting mass balance, we feed 1,000 kilograms of whole moringa seeds into this primary module. Module 1 outputs 260 kilograms of high-value cosmetic virgin oil and leaves 750 kilograms of raw waste cake. Because this is a continuous physical process, the operational velocity is high. It processes the entire ton in roughly 4 hours. Module 1 secures immediate revenue, but the ultimate success of the refinery hinges on how we process that remaining waste cake. We pass the cake to Module 2, Acoustic-Enzymatic Extraction, or AEE. This was engineered specifically to replace the industry standard of using hexane solvents. The core physical mechanism is a 20 kHz titanium ultrasonic homogenizer introduced into an aqueous mash of the waste cake. The probe causes acoustic cavitation. The energy creates microscopic bubbles that implode with enough force to shatter the plant cell walls. Simultaneously, we inject precise loads of cellulase enzymes to digest the shattered structural fiber. We then add pectinase to break down the cellular glues holding the internal matrix together. This targeted biological digestion releases the remaining trapped lipids directly into the solution. Combining the physics of ultrasound with the precision of biological digestion achieves yields of 35 to 38% without explosive chemical risk. At this stage, the AEE output is a complex emulsion of industrial oil, water, and solid mass. Standard gravity settling is too slow to separate this specific mixture efficiently. We route the emulsion into a 3-phase disc stack centrifuge. This module uses centrifugal force to rapidly spin out and isolate the biofuel-grade oil. This creates a production bottleneck. AEE is a biochemical process taking up to 12 hours, clashing with the press's 4-hour speed. We resolve this through asynchronous scheduling. We run the mechanical module continuously while the biological reactors operate on staggered parallel cycles. Decoupling the continuous physical steps from the batch biological steps resolves the volumetric bottleneck and maximizes daily throughput. Now, shift your focus away from the oil and toward the solid mass left behind by the centrifuge. From our initial 1,000 kilogram input, 640 kilograms of solid material remain. This is no longer raw waste. The enzymatic digestion and fermentation processes changed its composition. The process successfully neutralized bitter anti-nutrients and pre-digested the complex structural fibers. Treating the cake with enzymes upcycles a low-value waste product into a highly bioavailable, premium animal feed. This establishes a third distinct revenue stream. This Sankey diagram visualizes the final mass balance for a 1-ton input, revealing exact volumetric outputs. Stage 1 virgin oil sells at cosmetic premiums. Stage 2 secondary oil enters the biodiesel pipeline, and the 640 kilograms of protein meal enters the feed market. A standard mechanical press architecture yields roughly $1,478 in net profit per ton. The 2-stage Drueppel Gemini Biorefinery yields $7,612 in net profit per ton. This ROI increase is the direct result of executing systems poetry. By respecting biological parameters and decoupling our methods, the waste of one module becomes the precise input for the next, closing the loop on architectural efficiency.